Hi, everyone. Welcome to today's session. So today we have Chris Reinke here to present for us his recent work on transfer reinforcement learning. So Chris is a researcher in the robot learning team of Xavier Alameda Pineda at Inria Grenoble, where he adds the learning robot behavior work package of the European Horizon 20,000 to 20 Spring project. His research focus is transfer and meta-reinforcement learning methods and their application in social robotics. Before, he was a postdoc at Inria of Pierre-Yves Gaudier, located in Bordeaux, working on automated exploration methods of complex system behaviors. He received his PhD in 2018 about brain-inspired reinforcement learning in the Neural Computational Unit of Kenji Doya at the Okinawa Institute of Science and Technology. Before his PhD, he did a bachelor's and master's in cognitive science at the University of Osnabrück, Germany. So today he will talk about successor feature representations, human-inspired transfer RL, and its application to social robotics. We're very happy to have you here. Thanks.
Yeah, thanks. Thank you, Okan. Thank you, Okan, for the introduction. Thank you, Sugiyama-sensei, for inviting me here so nicely. You have a very nice location in the center of Tokyo. When I was in Okinawa, it's very different. You can see forest and the ocean. So today I want to talk about our recent research in meta and transfer reinforcement learning and how we would like to apply it to social robotics. So the talk, I will also talk a little bit more about the brain. So I will show you there's a strong connection between machine learning and reinforcement learning in the brain. And then we will see what the successor representations are. And I will basically show you that they are also a good model for human decision-making. And before going towards how we use them in the AI and in the robotics possibly. Okay. So the machine learning and the brain, we have like a lot of connections basically. So this is a paper by Kenji Doya, my PhD supervisor. And so in 2000s, he made this theory, or he showed that we can find our machine learning algorithms, we can find corresponding areas in the brain. So for example, reinforcement learning, what we will be concentrating on, you can find that the basal ganglia and the inner brain structures, they very much resemble reinforcement learning algorithms or how reinforcement learning works. But you can also think of the cerebral cortex as an unsupervised learning, basically mechanism, and the cerebellum as a supervised learning. So with reinforcement learning, I will not go too deep into the theory of reinforcement learning, but just to basically introduce you quickly the important things. So here I will talk mainly about value-based reinforcement learning. And there the idea is you have a system that you want to control. So you have the system has states and you have actions, and you would like to optimize the system to receive a lot of reward. And what we will learn all the time is this Q function. So, and the Q function tells you what is my expected future rewards in the next steps. If I do in my current step a specific action, and then I follow a certain policy pi. So I follow a certain behavior. And then this function tells us what is the expected future reward I would get for this behavior. And we can use this then basically to decide what we do in this state here by basically taking the action that maximizes this Q function. So this is the idea of these value-based reinforcement learning. We can also nicely represent this by saying our Q value is just our next reward plus the Q value of the next step. This is kind of the Bellman equation, the famous one. And we can basically learn this by using these temporal difference learning mechanisms where for example, we're having a current prediction of a Q value. I'm in the state, in this action, I have a prediction of it. Then I'm making a transition. I go to the next state with a certain action, and I observe my reward. And then what I also take into consideration is my expected Q value from this point on. And basically, this becomes now my observation, which you then can compare to your prediction. And of course, if there is a difference, then your prediction was not correct. So you have to compensate with this by by changing your Q function to go towards this observation. So this is these temporal difference learning mechanisms. These are kind of model-free learning algorithms, because here we don't have a model of the world. So the only thing you are learning is what is the expected future reward for a specific action that I could take now. So you don't know what this action will do in the world. You only know it would maybe bring me a certain amount of reward in the future. On the other hand, we have these model-based reinforcement learning algorithms, where we basically are given, or we are learning a model of the environment. So this is basically, if I'm in state S, I take action A, what's the probability to go towards state ST+1? This is my world model. And then, of course, we can build like these trees. So I'm in the state, in the blue state, and then what's the probability of ending up in these different successor states here with specific actions. And of course, if I have such a model, now I can also compute my Q function, my expected reward I would get for doing a certain action. And here we have to sum over all our future states we could get into. And then I take into the consideration the probability of getting there with my current action, actually. And then you basically can sum up the reward and the expected next Q value. So this is a model-based reinforcement learning. These are these two like major types of RL.
Do you assume the reward function is known?
Here we would assume it, but you could also try to learn it. Like it's up to the problem. Yeah. In many cases you learn it, but in our cases we often we assume we know it because we do robotics, and in robotics I design the reward function. So yeah. Also, so this is, for example, often used also in like AlphaZero. So in these games, and of course in the game you also know the reward function. So and so yeah, so the interesting thing is that we can find for all these reinforcement learning algorithms, we can find brain areas that resemble them, or that show that similar mechanisms are going on in the brain. So here we have one piece of evidence for these model-free reinforcement learning. And if you remember, in the model-free reinforcement learning, we had this TD error, where we compare our current estimate, what I expect, to what I actually get. And this we call the TD error. And we can actually find this TD error also in the brain. So here we have recordings from some monkeys, I think. And the monkeys, they're basically getting sometimes a light signal, and then comes a reward, like some food or some water. And here we can see the spike pattern of some neurons. And what happens is the monkey sits, and there comes now, there's no light given, so the monkey doesn't expect anything. And the monkey gets some reward, which is very unexpected. And you can see that when the reward is given, we're having a high activation of these neurons. And this is basically the TD error, because the monkey didn't expect anything. So there is a high TD error. But after some training, and when we tell the monkey, so first there comes a light on, and then a second later comes the reward. What we can then see is that when the light goes on, we get then this high activation, because the monkey didn't expect the light. You know, it's like randomly the light goes on, and now we're having again this TD error. What we can see now is that at the point where the reward is actually given, we don't see this anymore, because the light now tells the monkey basically he can expect a reward. So the TD error is 0 anymore. Interestingly, we can then also see what happens if we don't give a reward and we put the light on. So if we put the light on, again, it's an unexpected state. So there's a high TD error. But then if we coming to the point where we would give normally the reward, and the monkey expects the reward. Now we have a depletion of these neurons. So the TD error is kind of negative. So by this, we can see there's some neurons in the brains that reassemble this algorithm of this model-free reinforcement learning. We have also some evidence for model-based processes. So here it's very early from Tolman in 48. This shows basically you take a mice or a rat and you put them in these kind of mazes and you let them explore around randomly. And there is a box here. And if the mice or the rat reaches the box, it will be taken out. And for some mice, there is food in this box. And so we can see here, where's the food? Here's the food reward. We can see that over the days, the number of time or the time the mice needs to get to this box decreases slowly. So the mice is learning to get there. But if we give no food, then you can see it learns a little bit, but then it stagnates. It's this curve here. But now the interesting condition is, what if we, for the first 11 days, we don't give food? So there's nothing to learn. So we see the mice, they follow the same behavior, but then we give food. And then we see here a sharp learning. So the mice basically immediately can learn to go directly to the food box. And that shows you that the mice, they kind of acquire a model of the environment, of the world. And if you once give them reward, now they can use the model to go quickly to where the reward is given. So this is some evidence for these model-based processes in animals. Here's an interesting experiment, and that shows how do we, so now we have these model-free processes, and we have these model-based processes. And the interesting thing here is, how do we actually use which one at which situation? And here's some evidence that it depends a bit on how often you do a task. So we usually associate model-based processes with goal-oriented behavior, because with the model you can have a goal and you can go there. Whereas these model-free processes are more habitual, because if you remember, the Q function tells you just how good an action would be in terms of reward. So but you don't know what will be the outcome of it. So you will, if you can do the action and the action, predicted you a high reward, you will always do it. It's like a habit. And we can see this here in this experiment. We're having a mice which can press a lever and gets a reward. And we have two conditions. Once you train it for 500 trials, once you train it only for 100 trials. So that's the only difference. And then comes either afterwards a devaluation phase, where you give the mice a lot of food or you don't give them a lot of food. And of course, if you give them a lot of food, they are not hungry anymore. In principle, they don't want to have this reward anymore. And then we're coming to the test phase, where you actually sit the mice in front of the lever and you see, is it still pressing the lever or not? What we can see is that between these two groups, like a lot trained and not so many trained, if we don't devaluate, so the mice are still hungry, then these are the white bars, then they usually still press the lever. So, there's no difference between these. But what happens if we feed the mice and the mice is now well fed, not hungry? Then we see if we overtrain the mice with 500 times, the mice is still pressing the lever. But if we don't overtrain the mice, now it's not pressing the lever anymore. And this seems to show that in the overtrained case, the mice acquired a habit. And it seems that the model-free system took over, because the model-free system only takes you, this action is good, but I don't know what is actually the real environmental outcome of it. Whereas in the not so overtrained case, seemingly the mice uses the model. So the mice can now say, I press the lever, there comes food. Do I actually want to have the food or not? So we see there's this arbitration between these processes in our brains going on. So with this, basically, I want to show you these processes in the brain. And for me, interesting is now, what if we want to transfer also some knowledge? So we come to transfer reinforcement learning now. And so transfer reinforcement learning just means how can we use knowledge from some learned source tasks to a new target task. And here we're having, for example, a situation for us humans. We learned already in our environment that there are different, restaurants or shops we can go to, like a burger shop where we can get food. There's coffee is okay, but the atmosphere is also okay. But the cafe, for example, the food is not so good. Coffee is great. Atmosphere is great. And now we are often having new tasks that we have to solve in these environments. So one day I'm hungry, so I value the first item, food, very high. Whereas on the second day or later, I'm groggy, so I need some coffee. And so the question is now, how can we quickly switch between these different behaviors that we learned to go to these coffees, depending on our task and on also new tasks? This is basically the idea of this, the successor features that we are coming to soon.
What is the task in this case? Three different tasks.
Yeah. So the task is just to maximize your reward. So your reward would be you multiply these values with the items, the product. Yeah, it's the product. Yeah. So here it would be just a maximize coffee.
Isn't it more natural to formulate this as a multi-objective reinforcement learning?
Yes, you can use these things too, but here the idea is more how do I quickly adapt to a new thing. Yeah, with the multi-objective, you try to always learn the Pareto thing. You also like to learn this here, but here the focus is more on how do I quickly find a new solution if given a new task. Yeah. Whereas in multitask, you train, you basically have already all the tasks there and you train over them. Whereas here the thing is, what if I give you now a new task and you have to find the optimal solution for this?
Is it essential to have three different aspects in this case?
No, you can have as many as you like.
But you need multiple aspects.
Yes, otherwise it would be normal reinforcement learning. Yeah.
Okay.
Like yeah. Yes. Yeah.
And these numbers, let's say this 1, 0, 0, or this simplex, like, is it a state for you, or?
It's like a context. Yeah. Like you're giving a task. That's kind of your tasks. Yeah. Higher level context.
And each particular problem might have its own state or something.
Yeah. So in the problem, you would be maybe on a map, and then like your position in the map would be then more your real state, which we would use in reinforcement learning. So to make things more concrete, so here I show you first kind of a behavioral experiment, how humans are solving this. So this is by Tomov quite recently. So they use this two-step task where instead of these restaurants, you are given these three kind of resources, wood, I don't know, stones, maybe coal, I don't know. And then in the beginning of a trial, they tell you how to evaluate these resources. And you are asked to maximize basically your reward, so the amount of money. And then you are in state number 1 and you see 3 doors. They're always the same in the state. And then you can make a decision for one of the doors. You go to the next and there's another 3 doors. And at the end, we basically, here we see how much of each resource we are getting. So it's again 3 resources. So here we would get 10 of these stones, but nothing else. And then, the question is, you should be optimizing this to get the highest amount of money. The people are trained over 100 trials, and at each trial, they give you one of these 4 kind of tasks with these weights, and they are randomized per trial. And then comes the important thing. After these 100 trials, they give you 1 new task. And so then they would like to see what option do you choose for this new type of task. If we look a bit more into detail, we can see that if we would always choose the optimal arm, then for our training tasks, we would usually use arm number 6 or arm number 12. And this is then also, if you think of optimally solving this, then you can use your model-based system, because with the model-based system, I know where the doors are leading, what I can expect there, and so I could optimize this perfectly. If we think of a model-free learner, they basically assume the model-free learner is very simple, and the model-free learner only learns to optimize the average over all tasks. So regardless which task you are, it basically learns a Q function, but the Q function is over all tasks. This would then be the optimal arm, would be number 11 for the training trials. Everyone else would give you a negative outcome. And now comes the interesting thing in the test case. If you look at the optimal arm, it would be, or door, it would be number 7. So if we would use a model-based system, number 7 should be our outcome. But if we use a model-free, then most probably we would choose number 11, because that's the optimal for the model-free at the moment. But interestingly, what we see is that the humans don't take either of these, but they choose arm number 12. And so now the question comes, why do humans maybe choose arm number 12? And for this, basically, we are coming to this theory of successor representations. So that's the model that people think is maybe going on. So what are successor representations? They were introduced by Diane in the 90s, and it's not so complicated theory. It's basically a discounted state visitation frequency. So that means I'm in a state S, I do action A, I follow a certain behavior, and then we measure how often do I visit a state S prime. So how often do I get in a future state, certain future state, and that's my visitation frequency. And of course, we can write this down here with this probability of getting there at a certain time point. Yeah. So this is basically what we are learning in these successor representations. We can also learn this with our normal temporal difference update, because if we get to a certain state, then I assume basically the probability at this time point is now 1. And I use this as my kind of target that I observed now, and I learn this, the successor representation. And given this, we can basically then compute our Q values based on it. Because if you see, our Q values is just the expectation over our future reward, over the future steps. And if we write this now down with the probability, so then we get, we have to sum at each step over all the possible successor states that we could get in there, take their probability and multiply it with the reward we would get for getting into the state. And this basically is the same as our discounted state visitation frequency. So we can recompute our Q values with this. And so now the idea is here. So now the idea is here.
You said your potential applications are robotics.
Yes.
But do you handle state as a discrete variable?
So here it's discrete. Later we come to a bit continuous. So yes, so we would try to use continuous variables. It's not so easy, but
one function, indicator function might be a problem.
Yes, yeah. So these are problems. Yeah. We will come to this a bit later when we go more to the AI thing. But this is basically a problem with this early theory of successor representations. Yeah. So now the interesting thing is that, as you can see here, I learned maybe my successor representation, and now I could just plug in any reward function, and I can compute my Q values. So the idea here is that maybe we are learning specific behaviors, so which is our policy pi, and then given a new task, I can basically then reevaluate these different behaviors I learned for this new reward function of the new task. And I can say which behavior is the best now in this new task. Yeah.
So this is as difficult as learning a model, right? So if you have the model, you can get this M of pi. And likewise, if you have M, I guess you can extract the model from it.
So the model is maybe a bit more complicated, because the model you have to learn for each state and action pair, the exact true model. Yeah.
But you also like index by SDAT, right? For each state and action, I need to.
Yeah, you need to learn something, but it seems to be this is a bit easier to learn in a sense. Yeah. Just in the practice, yeah, because it's a sum over future things, and usually it's easier to learn sometimes the sum than the individual things.
Okay.
Because the individual things can be very, they can go up and down, so there can be a lot of discontinuity in the model. So that's yeah, it's very noisy. There can be discontinuities in the model, whereas if you take the sum over something, it's kind of the average over the future. This makes it more smooth, and it's easier to learn these kind of functions. So if we look now in our problem here, so the idea is now that we compute our Q values with these successor feature functions, representations. And what we're doing is we basically try to identify our previous policy that maximizes now our Q value for the new task arm. And so what you have seen before is that in our previous tasks, humans learned usually that number 6 is optimal and number 12 is optimal. So they learned this over time. And what's now happening is that humans seemingly, they now only choose between these two strategies, which is the optimal of these given a new reward function, because they most probably acquired some idea of what is the outcome of these two behaviors that they learned already. And this is what we, this is basically what we observe. So then humans take door number 12. So it's one of the previous policies they learned.
So they learn this M function.
Yes, so that's at least the hypothesis here. Yeah. Yeah. Or something similar to the M function, it's not, yeah. At least what they are learning is that I learned already these behaviors. I know more or less what will be the outcome of them. Now I'm in a new task. Now I can compare my previous behaviors and their outcomes to what would be best in this new task. That's the idea. Yeah.
And once they learn, let's say, something like this M function, then they actually choose a suboptimal solution. Then, right?
Yes. Yeah.
Okay.
So yeah. So humans are not optimal. So that's not always. Yes. So with this, I'm basically at the end of this more brain-inspired part, and we're going a bit more towards the machine learning and robotics. As you saw, there's already these successor representations that are introduced from Diane in the 90s, but they're basically not really applicable to high-dimensional state spaces. So what we had already discussed a bit. That's why in 2017, or actually a bit earlier, there was these successor features introduced, and they now allow to use these kind of methods also in high-dimensional continuous spaces. But the problem is that they basically restrict the problem to reward functions that are only linear, kind of. We will see this. And that's what we try to hope to overcome with what we are doing in Grenoble. Okay, so again, these successor representations, it's the state visitation frequency of future states, given your current state, action, and behavior. And the problem is what we already saw is that to compute the Q function, we have to iterate here over discrete states, over all the states in the future. And of course, if they are discrete and only a few, you can use a sum. But what if we're having a robot with a camera? So now our future states are camera images, and they are continuous and basically infinite, many possibilities. So in this case, we would need to have an integral over the future states to calculate this. But it's very hard if they are high dimensional. So this was usually never used for these kind of cases. For this, basically successor features were introduced, and I want to basically show how they are used on this example task. It's a 2D grid world. You start in state S, you have to go to the goal state G. But on the way, you you can collect some objects of these three types here. And the tasks, the difference between different tasks is how much reward you would get for each object to collect them. So, for example, we're having our task 1, and this task, you get a very high reward for collecting the red object. And maybe the agent over some time, it learns this red policy. So collecting these two circles and then go to the goal. Just to mention, the agent will not collect all the circles because the goal will give you also a reward, and we're having discounting. So the longer you need to go to the goal, the less reward you get from the goal. So that's why the agent does not like collect everything and go to the goal. Then we may be having a second task where we collect these triangles. Again, we can use this path here. Maybe a third task where we have to collect the rectangles. So we maybe do this a bit longer task path. And then we're coming to the interesting part. And that is, what if we're having now a task where we would like to collect a combination of these objects. So maybe triangles and then maybe rectangles. So the idea is now to use this successor representation idea. So to combine your previous solutions. So what happens is basically, I know already that I learned a behavior, the green behavior, to collect triangles. And I can evaluate that this is good in my current task. So why not choose this? So the agent would go towards collecting these triangles. Nice, nice, nice. Of course, I could now just go to the goal, and that is it. But at this point here, the agent could also then say, wait, I'm here. From here, my behavior of the task 3 was to collecting these rectangles. So why don't I switch to this task now, to this behavior? Because it gives me 2 rectangles. And this is basically what we hope to achieve in these successor features. So how do we do this? So the first assumption is that we compose our rewards out of these features and these weights. And it's a linear combination. So what are the features? The features here would be, do I collect at a certain time point a certain object type? So it's a binary vector. So if I collect a circle, I would get 1, 0, 0. Then our weights are just the weights I showed you. It's like in task 1, it would be 1, 0, 1, 0. And then, of course, I can just multiply each weight of the corresponding item with the feature for this. And of course, we can just summarize this with the product here. So this is how we construct our reward function. So if we now look at our Q function that we're always trying to learn or we try to represent, we can simply, as you know, it's the sum over future rewards. So now we can plug in for each of the rewards this formulation. And what you can see is that the nice thing is that these W, the reward weights, are constant at each time step. So they don't change. And because of this, we can basically pull them out of the sum over time steps. So now in our sum, we only having basically a sum over discounted feature vectors. And if I multiply this and make the product with our weight vector, then I can recover the Q function, the Q value. But
here's the question that I missed out. If let's say the objects would be moving, then
you
wouldn't do that, right?
No. So all these successor representation theories is only for environments where only the reward functions are changing. Mm-hmm. So if your dynamics are changing, you're having trouble. Yeah. But you can combine this. It's not so there's some universal successor features. It's the name where you learn kind of a meta policy over different environments. We take in the environment dynamics, and then this function tries to predict how would be the features are in this new type of environment be.
Yeah, we need to construct something that is invariant, right? About the environments.
They are moving, let's say, but they are moving with a certain velocity or in some way that helps us to predict, right?
Or at least that is kind of conditioned on something where you can then predict their movement or their location. So basically now we can reconstruct our Q values, which we use to make decisions. So now we can see how we solve this. Basically for each task that we're learning over time, we're learning this C function. So the C function again is just this sum over future successor features, these feature vectors. We learn this for each task, and basically then we're using these what is called a generalized policy improvement method. So at each step, instead of just looking at my current Q function to make a decision, we're looking also over all previous policies that we learned. And we basically identifying how would this policy behave, or what would be the expected reward for this policy for my current task. And then you select the policy that gives you the highest action, and of course the highest action of this policy. And by this, we basically getting the switch here. Because we first see in all these states in task 4, we see that the green, so P2 policy would be good. But then at this time point, we check again, and then it sees, now this P3 policy would be best. So then you follow this one. And this is how we can do this transfer of knowledge. So here are some numerical results. I will not go into the different algorithms. This is you can see this is over the tasks trained. So we're having like up to 250 tasks here, different tasks trained. Important is here Q-learning, which basically is just your standard Q-learning algorithm. So for each task, it learns new to solve it. And this here in the upper one, it shows you the average return divided by the number of tasks. So it's your average return in general. And we can see that, well, Q-learning, it needs to learn, and then it basically has a certain average return for each task. So that's kind of a baseline. So you can also see here the return per task, and we see that the Q-learning goes up, then it's a new task, and it usually goes to a similar level of reward it can acquire in a task. But if we compare this now to our successor feature, Q-learning, which learns these C functions and then does this 3PI procedure, we see that after 2 tasks, it basically exceeds the performance of the Q-learner. And then it can actually go at like 6 times of the reward at the end. These different algorithms here, these SFQL8 and 4, they are also when you try to learn the features itself. So you can also try to learn what are the important features in the environment and use this. So now I'm coming to how we would like to use this in our lab in Grenoble. So we are part of a European project where we have this social robot. And the overall goal of the project is that the social robot interacts with people, usually with groups of people. And our goal or our part of this is to do human-aware navigation. And we also would like to combine this with optimal recording of the audio while the robot is moving, or optimal sensing of the environment. So to combine these different subtasks together. So and of course we wanna use reinforcement learning for this. And if we want to use reinforcement learning, we need a reward function. And here the reward function usually depends on many components. You see, I already use here a bit like this features kind of again. And these components can be, for example, the distance to objects or the distance to humans. So you want to be, not too close to objects, not too close to humans, but if I want to get to humans, you still have to get to a certain distance. It can be the speed, the robot should be too fast or too slow. Or it could be the audio quality, like how well the robot is hearing at the moment. And then usually you create for each of these features or these components, you create like a sub reward function that evaluates this and you sum over all of them. So this is like a usual approach to do. But so for example, here we're having a reward component function for the speed, where I would like to define a certain optimal speed, like here 1 meter per second, no, not per second, but per minute. And then I use maybe a Gaussian around this to say, you know, like, let's try to get there, but I use the Gaussian. And then we can, of course, use different positions of the Gaussian if we want to have different optimal speeds. And so the problem here is that practically I can define a reward function, but usually this reward function does not work very well at the beginning. So because as an engineer, yeah, we start with a certain reward function, like give certain weights to these components, like how important is it to be far from objects. But then I train, so I need some training. I train on this reward function. The robot finds the optimal behavior for this reward function, hopefully. But then I see the robot is still bumping into objects because I maybe did not give enough negative weight on getting close to objects. So then I have to go to my next reward function and I have to say, maybe I give more negative weight on getting close to objects, but then the robot does something else stupid. So it goes too close to humans. And so you have this iterative process of maybe finding the optimal reward function. And one approach where we would like these successor features is to help in these situations so that you don't have to learn each reward function from scratch, but you can reuse your old knowledge by using these successor features to improve your learning speed. And here comes now the problem for us. And that is, I showed you, for example, we're having this reward function with a component where, you know, I put in the speed and I use some Gaussian. But the problem is with the classical successor features is that they are a linear combination of some weights and your feature. So that would be a combination of weight and the speed. But with this, I cannot define a specific speed I would like. If you put a positive weight, it's like as fast as possible. If you put 0, it's like don't move at all. So I cannot directly use this framework to specify a new reward function. And this is a problem for us, or that we would like to solve. So here we're having a toy problem that I use to also visualize this. We're having this environment with a toy race car. It always has to move, so it cannot stand still. It can move in circles or straight. Then we're having these 3 markers, and our features are the distance to the markers. So how distance is it to each marker? And then we can have, for example, a reward function, which is just a basically a sum over Gaussians that have certain preferences for locations from these markers. And then you can see here a example reward function. So the car should try to go to these dark areas and drive kind of around here. And if we now compare here our normal Q-learning learns something, you know, it's kind of the baseline. And we now throw in our successor feature, where I try to approximate this function with a linear model. But, you know, it's not very good to approximate a Gaussian with just a linear combination. Then you can see now the performance is worse than the normal Q-learner because it cannot really model these rewards. So it cannot do a good transfer. And yeah, so here we're coming to how we would like to solve this. It's not very complicated. It's quite easy. So this is these successor feature representations that we propose. And the goal is to allow now these general reward functions. So instead of this linear combination, we would like to have any R. And how we do this is we basically go a step back from the successor features to the successor representation. But the only thing we are doing now is that if you remember in the successor representation, we used the state visitation frequency. So we're thinking about states. But here we're only thinking about features now, and features are usually low dimensional, and that helps us to actually learn these functions. So the idea is here that if we think of the Q value, it's the expected reward we would get. And then, of course, to compute this, we would need now, for each future state, we need to know the probability that at this time point t, or t plus k, you are in a certain feature. And then you multiply this with the reward you would get for being in this kind of feature. And this is basically the whole trick. Now you can see again that this R doesn't depend on the time anymore. So we can somehow get it out of the sum of the time. And in our sum over time, we're now having these kind of a sum over probabilities, discounted probabilities. So this is basically these Xi, what we try to learn.
So these features, why are they like then moving over time? Because you say to be in a certain feature at certain times that.
Yeah. Well, depending on your behavior, they change. Or like depending on the behavior of the race car, the distances to the markers are changing.
Okay. Yeah.
Yeah. So you have to learn that in the next time step, the probability of being 1 meter away is, maybe like 0.9, but in like 5 time steps, it's like 0 more or less because you went.
Like a compact state.
Yeah, the features are kind of a compact state representation, which are then used just to compute the reward function. Yeah. But by this, you don't need the full state. You don't need a probability distribution or learn this function over the full state. That's the basic idea. So it's not nothing too complicated in the end. Yes. So the thing is, we would still need here an integral over features, if they are continuous. So in a lot of cases, if we have discrete features, we can get around this by using a sum. But in the case of continuous features, in the examples that I'm giving, we discretize them. So we say, the features is usually from 0 to 1 in a certain dimension. So I create 10 bins. And so by this, I discretize them. And at least for these tasks, it's working. Yes, so for discrete features, how does it learn? It's basically if you give me an observation, so go from state S to st+1, do action A, and you see a certain feature. It's again this TD learning algorithm. I basically now assume the probability of seeing this feature at this time step is 1. And then you basically can do your TD algorithm.
So for the continuous case, you just discretize and you still do.
Yeah, in this paper, I just discretize. Yeah.
What you could also do alternative things like it. Like
Yeah.
Gaussian or something. I don't know if that makes sense, but some other ways to move to by parameterizing.
Yes. Yeah. So so there's like some approaches. So maybe 3 or 4 papers where people try to look into how to do this. I'm also looking into this at the moment, but you can basically just try to learn it over the continuous feature space. It's possible, but it's learning the functions is a bit more harder. Yeah. And so how basically the networks are looking, here it's simple. You give in your state, you have some neural network, can be deep, can be not so deep. And then basically for each possible feature that is possible, so it's now discrete, you basically give out the Xi value. And then at least in these examples here, we're having for each possible action, we're having a different network. And if we look at some of the results, so here we're using a similar scenario as the one that I showed you before with these objects, but I had to change it a bit. I had to introduce here now kind of that objects can have a form and they can have a color. Because previously you had just 3 different types of objects. And what I wanted to introduce here is general reward functions. So reward functions that can be over features, but not linear. But if I have only 3 object classes, every reward function is kind of linear combination. So I cannot create a general nonlinear reward function, but here we can. And so basically what we can see here now is that if I use these general reward functions, we have Q-learning as our baseline, and then we see that we have our successor feature. We can see that it performs better than Q-learning because the reward functions here, they are not too nonlinear. So you can often approximate them using a linear combination. So that's what I'm basically doing here. For each new task, I try to learn or approximate the best linear combination for this reward function, and then I use this. But if we use actually this successor feature representation, which doesn't care if something is linear or nonlinear, we get a better result. And we can also see here if I use specific types of reward functions. So here I learn a linear model for these reward functions, and I look what is the error for this model. And we see that if the model error is low, so we have reward functions that are near linear, we see that this difference between successor features and successor feature reward is more or less the same. So it's like 1. But if the reward functions become more and more nonlinear, then the performance of the successor feature drops to like 50% here of the successor feature representation. So it shows there's this problem with this linear reward functions. Interestingly, if we also look at linear reward functions, there's actually also improvement of the successor feature representations over the successor features. It's a bit unclear why for me at the moment, but it seems that it's maybe connected to maybe distributional reinforcement learning. This is where instead of learning just the Q value, which is a scalar, you learn the distribution over the Q value at each time step. And it's shown that this also improves already learning. And it seems that because it's a higher than, because you have to learn kind of the distribution, you have more information that goes into these networks. And it helps maybe with the gradient to control the gradient. But this is a bit unclear why this is the case here. When we look at this toy example here with the razor now, we have these Gaussian reward functions where the successor features are not very well attuned to. Now we can basically solve these tasks better than Q-learning because we don't rely on this linear relationship anymore. We also show some theoretical results, which I will not go too much into detail. So the first result is we show that the convergence of the algorithm, so basically given enough time to explore around, and if your kind of learning rate is optimally tuned, then you will learn the optimal solution eventually with these C-learning algorithm or this successor feature representations. This follows more or less the proof of the normal Q-learning. We also show a bound on the transfer performance. So that is what would be my expected performance given a new task. If I do a zero-shot transfer, and again, I will not go into detail, but what you can see here is it's basically depends on what this Ri here is the reward functions that I saw in the past. And basically it depends here, we're searching the task that has the closest reward function to my current reward function. And that determines my performance. So it's basically, if I had a task that has similar rewards before to my current reward, then I get a good transfer usually. I mean, it's very clear, but you can make it formal. Yeah, with this, I'm basically at the end here with these. So again, as takeaways, I hope I could show you that there's a strong connection between these machine learning and reinforcement learning processes in the brain, and that we can learn from each other. And that one of these is these successor representations, where the key is that we basically learning different policies, and then we're learning what would be the outcome of these policies or behaviors. And by this, we can then use in a new task where we get a new reward function, we can evaluate them, which of these is now optimal in this new task. And we see that humans seem to do similar things too. So it's kind of inspired by human decision making. But in AI and robotics, we can use it too. But the old successor representations are not very applicable for high-dimensional state spaces. The successor features, they're kind of limited to these linear reward functions. And we hope to solve this a bit by going towards these successor feature representations. But it's a kind of also ongoing work. Yeah. And with this, I want to say, let me see if I have. Yeah, so basically we are at the end. So with this, I want to say thank you. And if you have more questions, please feel free. Yeah.
Yeah, I was wondering, like, computationally,
so computationally, you are actually using a deep neural network to learn the Q function, right?
Yeah.
But with regards to the features, I guess because you design them, you don't actually have to do some computation there.
So we learning not the Q function, but we learning the Xi function.
Yes. Okay.
Yeah. But you have to know the features. So in our case, because we are in robotics, for us, it's always, I know the features. I know it's like the distance from these obstacles, or it's the distance to humans, or so by this they are given, but you could also learn them.
And exactly, as you said, you kind of design the reward function there in that integral, and then you kind of learn this C5, right?
Yeah.
With a small network, let's say.
Yeah.
And then you kind of have to integrate it yourself.
Yes. Yeah. Yeah.
Okay.
Yeah.
Thanks.
So there's basically, so our reviewers, they are always, they don't like that we think with the features are already given. So they would like to see, can you learn them? Yes, you can learn them, but usually if you learn them, your performance drops drastically, like by half, because the features are not optimal than usually learned. And you also need time to learn them. You know, it's not like they are given.
But you showed an example where there was a plot where the features were learned, right? So
yeah.
You could also apply it in your framework.
Yeah, of course we can apply this in our framework. Yeah, but yeah, so it's not our focus. But the reviewers, they really like this part, and so they always stress what's with learning. And so the interesting thing is actually if you learn them, you can also overcome this non-linearity in the successor feature framework. Because if you think of it, you can, the features that you are learning, so we're having, we're having our features here. Here, of course, they are kind of creating, you know, it's a very linear, because it's like 1, 0, 0 would be the feature for a red thing. But the features itself could encompass the non-linearity of the reward function. Like, it's basically that you can learn features in the case of this function here. You could learn features with which you could express this, but where the feature is not just the speed, but it has to be, you know, something which encompasses the non-linearity itself. And then you can basically also apply this to non-linear reward functions, but then you have to learn the features. And of course, if you are in a new task where kind of your reward function uses a different non-linearity with these features, then you have to relearn, you know, because it's not in the features itself. But also if you change the features, then your old C functions, that you have learned over the features, the stage, visitation, frequency, they becoming basically, untrue because you change the features itself. So it's hard to. So yeah, so it's it's nicer if you know the features from the get-go. And
Thanks for the nice talk.
So initially, you started the talk based on some neuroscientific findings and motivation.
yes.
But in the end, so everything is computational to me.
Yeah.
So what was the real role of neuroscience in this project?
So for me, it's usually kind of a inspiration. So where I start from. So, I saw that humans making these kind of decisions. So then for me, it's interesting, how could we create similar processes on the machine? So it's more for my personal, it's not really in the project itself. So it's not that we use directly neuroscience or we go back to neuroscience. Yeah.
So this is my personal preference. But like, it seems to me that neuroscience is used for kind of an excuse to avoid proving something mathematically.
Okay.
This is brain funny, that's why it's good. But we don't prove any convergence.
Okay.
What do you think about that?
Maybe it's nice to fill your introduction, like the introduction part of your paper.
I really want to know whether this converges fast.
Yes.
Somebody says this is brain inspired, so that's why it's natural and it's
Intuitive. It says on intuitive.
Yeah.
I agree that it's a nice motivation, but other guys are working, tackling the same problem in a really mathematical way.
Yeah.
So in the end, we need to somehow compare these two different approaches.
Yeah. I mean, we did some, like some theoretical results. But usually I guess it's to bring in new ideas into the field. Of course, you can also look from the very mathematical perspective, but maybe coming from the brain, you bring in a few new ideas, and maybe it can also help just to get ideas, basically. But it can also, the other way around would be that then in neuroscience people are interested in maybe these more mathematical theories, and then to search for similar processes maybe in the brain. Maybe the brain does it in a different way, in a more.
Can you also consider the other way around? So does your work contribute to neuroscience?
Well, I hope maybe in the future. So that would be. For example, if we then think more about the details, how do we learn these C function, for example, then you can think about maybe, there should be special processes to learn this. And then you could look in the brain if these processes actually exist. But I have not now a very specific detail I can point you at the moment. Yeah.
Okay, thank you very much.